So exactly, let's move ahead. So uh, the very basic, if I take upon is means if we try to see that means the history of this domain. So this is a kind of graph, or this is a kind of trend we can see here. So machine learning is somewhere lying in middle, and if we try to see a bigger block upside is you can say a superset is with the name artificial intelligence, and it's showing that it has an history of somewhat more than 70, 60, 60, 70 years. That the term was coined somewhere in 1950s, means it's a day old term. So and certainly means when we talk about machine learning, so has been one of the subsidiary means terminology coming out from this artificial intelligence means idea itself. So let's look on it. How does it come from there, and what does it mean exactly? Talking about this this figure and this trend itself, it's not mine. It's been taken from some source. Exactly. So now, so this is the artificial intelligence is the superset to machine learning. Now, how we come up to this machine learning and to very new names like deep learning in today's world. So how this was driven exactly? So we are well aware that means it as the trend is showing that was coined in somewhere in 1950s, and we had seen the artificial intelligence means many of the good researchers and good authors of the time as like means Rich and Knight and all means they had seen the evolution of artificial intelligence, and how was the artificial intelligence seen at that time in 60s and 70s. So it was seen as somewhere like means in terms of some logics we been represented like means predicate logic and so on. So meaning that means so the intelligence was seen somewhere in terms of the rule based and the knowledge based. So we were having the knowledge represented as a rule based, and the inferences were made through an AI engine, which was actually taking those rule based as an inputs. Uh, so that was the time when it was this AI was in very simpler phase exactly. How means it grows up, and exactly what is the state in this time is we can see it like this means so so it is means intelligence. So what this we shall then understand about what is this artificial intelligence, and then only we will be able to actually means well understand how the progression has happened, and how the progression has to further go on. So this intelligence, artificial intelligence means if we try to elaborate it means word meaning of it. So it's well clear that means intelligence gained artificially. So for whom it is, we say that it is for computer and machines. So exactly this intelligence has been created for machines. So machine are one of the key element to this artificial intelligence. Another thing is means how this means machine will be made intelligent. So then we have to understand about means this scenario of means or an analogy means how this intelligence is actually created, or you say means who have the we know that the humans are intelligent. The intelligence that is somewhere God gifted to the humans. So how the intelligence is actually means, or it is like means it is by birth one is getting. So exactly it's not that way. So intelligence is not by birth, rather it is gained in time. Exactly. So how that happens? So we know that humans have the brain, and intelligence is gained there in the brain, and it happens means in a timely manner, in a timeline means the intelligence is gained. So intelligence is a label, or a state of brain exactly. So means if we try to see it like this, means when we were small kids, certainly the level of intelligence of ours was not that, means exactly, means we can say that, means at that time I was not intelligent or intelligent enough, you can say. And nowadays we had actually come up with some matrices also to actually measure this level of intelligence. So IQ or EQ or somewhat like that. So if we try to see a kid is having a, an intelligence level of zero, you can even say. So he or she doesn't know, means at very small age, means a kid but doesn't know anything of it, means what is this object, what is that object. And certainly if we try to see a small kid of 6 months who can means even not differentiate between anything, like means what is good or what is bad or what is being getting him harmed or somewhat like that. He can touch a flower in a means a fire in the same way as a flower he touch. So that is what the thing means. But later on he means comes to know about or understand that the things what harms should not be touched. So this is what the thing, that is the time when the this gaining of intelligence started. And certainly when this happens and this keeps on going, and we then grow up with the level of intelligence. Now we shall understand this means, so intelligence is gained in brain. Now the thing is how. So what is there which or so the process we shall understand, so by which this intelligence is gained. So this process is nothing but it's the process of learning. That is what in typical understanding we know. So this is nothing but it's learning. So in timely manner, on the timeline, we actually start learning things how means it's by looking on it, by asking something, getting answers to it, and so means this is means the learning happens by sensing around. ठीक है? So that is what the another important thing which is required to actually do this learning is sensing the world. And that can only happen through senses. And this is a god gift to us, that we have the senses, and certainly we can sense the world around us through these five senses. And through these five senses the learning happens. And means and certainly we gain on intelligence level. So senses are giving you what? So senses are giving means you the experiences, and that is actually the process of learning, which actually finally gives you a level of intelligence. So this is a process which we typically know about it in human being. So this is the process of learning which happens for the intelligence in human being. Now same can then be thought for machines. So when we say the means the intelligence has to be created artificially, so the same approach has to be then promoted. So this is what the thing is. So now when we are talking of means learning in case of machines, so this is nothing but then machine learning. Now almost the same process. Now when we say we have to come up with machine learning or learning in the machines, then we have to actually come up with a very defined means or a very defined process, exactly, you can say. So this process should be very much clearly defined with or mathematically proven, or you can say mathematically modeled kind of process that should be. So if we try to see it, so how it goes is like this. So, machine learning, if we try to see, we can actually define it as an entity of three tuples. This process can be defined as an entity of three tuples. These tuples are means performance, task, and experience. So how it comes to means these three tuples actually so so it's like this, means when we try to see this machine learning. So what this machine learning has to do, this process has to do. So this learning process has to actually improve the performance of a machine, of a system on a particular task, exactly. So P is improving the performance of a system on a particular task is important. So when we are saying the task is an important tuple, So performance is certainly we so learning actually improves the performance by improving your knowledge level or the intelligence level. Now for what? So is it that means we do learning so we will get expert in all the domains we will be getting means jack of all trades? No, exactly not. So learning can only be in a specific context, and that is what we are then is means restricting it to a particular. So improving of the means the performance improvement of the machine in a for a particular task, exactly in a particular context only. So that is very important. We can't make it as generalized means. So a machine can't be expert in everything, so it has to be an expert or is on a specific task. Now how it will happen is what is then required for it. So it, as in case of the human or means analogy, we can see it how the humans are actually means the learning is happening. It is through the experiences. So same way here. So experiences are required for means this machine learning process. What these experiences will be? So this is nothing but the data. So data required for a particular task, data involved in a particular task will be the experiences for this machine learning process in machines. So certainly means this field of study is making computers learn means without being programmed. That is what you say a change in the paradigm exactly, and so we can clearly differentiate it with a traditional programming. What was happening in the traditional programming was means we were having a machine. What it requires was we were to actually write or we were to make it train through a program. We were writing a program and then providing a data on that program to give some output. Then that machine was giving some output. But now what is happening in this machine learning paradigm is means we are nowhere worried about the program. So program is rather an outcome instead of an input. So what we have an input is the data and the output. So this is a complete set of experience or input and with an output label. So that this is an so actual input. So your experience is an actual input, and certainly what you get out as an outcome is the program on which this machine will be an expert for a particular task. That is what the thing which we say. So this program is nothing but your machine learning model, which is get means you are getting as an outcome. So now, all right. So this was somewhat intro in means the definition of the machine learning. Now another important fact to understand this means yes, it's a buzzword. So everyone thought of looking means to utilize it means knowingly or unknowingly also means. So it's like this means so we had heard this word, let's use it everywhere. So is it good to use machine learning everywhere, or is it of use uh, in every context and scenarios? So let's understand means so when to use this. So it's like this. So what are the scenarios and situations where this ML should be used? So very first thing is means so where the human expertise doesn't exist. So very first thing means if we are not having expertise, certainly we can actually look on machine learning approaches to do to drive something for us. So for an example, let's say this navigation on Mars. So we haven't gone there. We doesn't have any expertise about that Mars surface and so on. So let's go for machine learning. So we can value utilize machine learning for that space. Second thing is means let's say if the space where we are not able to actually explain our expertise. So it's like this. Means you can say a differentiation in vocal languages, like means um, I want to explain something to someone, but he's not able to understand my language, or my accent, or my way of explanation. So if such is a constraint, then certainly we can look for machine learning approaches. So speech recognition kind of thing, you can say. Another important space is like means. means when there is something to be customized, or when we look for a customized solution. For an example, in case of personal medicine, so means medicine, when we talk about the medicine prescription, it is very you say it is, it has to be much personalized exactly. And then in that case, yes, it is good to actually use machine learning approaches. So there is nothing like a rule-based inferencing solution we can propose for personalized medicine. So ML approaches are good for that. Then when where we have the huge data, so it's not actually easy to be manually processed. Then it is actually good to actually use the machine learning models. So this is what the thing is, where we shall use it. Or if we say that means so let's say we have a problem of like calculating payroll. So at all not it is good to use ML for that. So we have to actually look on the requirements and the space where we shall actually look use the ML. This is a good example to talk about. So let's say try to see it, the scripts for number two. So how different persons like two or these numbers. So 100% might write these correct this numeral in 100 different ways, and certainly means probably if we are not very much familiar to all those, so we will be getting wrong in actually identifying these numbers correctly. So that is what the thing. So if such is the case, certainly it will be good to actually use machine learning models for this kind of identification or recognition task. Now all these means the various kind of means example or the categories of the example which we can think for where machine learning can actually be utilized, or the learning algorithm can be utilized are so all sort of problems all around us means we can actually look into be categorized in these four different categories. Like means we can think of having machine learning being utilized for some recognizing patterns kind of problems. So this we can think of one category. So we can have multitude of problems which can be categorized into this kind of thing, means pattern recognition kind of things. So if you talk about means facial identities identification, biometrics, or you can say handwriting recognition is so all where the problems where we have some patterns to be matched or pattern recognitions has uh, so pattern are to be matched, you can say. So this is one category where we can use the machine learning approaches. The another is predicting something. So predicting, you can say the stock prices, exchange rates, or you can say the weather, you can say the power consumption in an area, or predicting rates of the power and different power companies, or XYZ, so on. So prediction. So having the past data and the current data means let's do prediction, interpolate or extrapolate some values. So this is another kind of or another category of problems where we can actually use machine learning. Another is means recognizing anomalies. So like means unusual credit card transactions. So anything which is unusual and large set of data. So it's like this unusual patterns in the sensor readings at different IoT platforms or somewhat like that. So this is another one category, and one of the very new category which nowadays we are actually looking on is so all remaining threes were all about means where the data was available. We were doing machine learning on the available data, whereas the machine learning here when we are talking about in case of this fourth category is all about means generating something. So it's like this means, so now we are actually doing AI for generating new thing means which is not existing. So generating patterns. This is nowadays getting more popular. We have so many kind of AI tools which are providing this kind of facility of generating patterns. So this is a typical categorization. Now, if we try to let's means look upon various state of art application, so we'll go in fast. So it's somewhat like this autonomous car. We have a good example of it. So from many years, means last 12, 13 years, we are actually looking on it. Means it started from Google cars, then we had seen a good means on-road examples of autonomous cars in terms of Elon Musk, Tesla, exactly. And then we are now even seeing it in our Indian markets, like means in Indian manufacturers, like means we are seeing it in Mahindra or Tata. Means not full-fledged autonomous, rather an scope of autonomous behavior. We are actually finding it there in these Indian manufacturers too. So if I give an example of, let's say, a very newly launched means Mahindra, that is BE6C. So it is providing so good features of ADAS and means autonomous parking kind of facilities, kind of things. And ADAS is coming in so many cars. We all know about it. So this is one pretty good example. Now, when we say autonomous cars, what is there as part of AI and machine learning, or what are the processes which are means actually involved for ML. So we have this terrain mapping. So laser terrain mapping is to be done. So huge ML is involved therein, means for classifying various different types of terrain through based on the this laser data getting received in real time. Then once we get this data, path planning is another thing which is happening, and certainly a huge ML is happening therein. Another thing is means adaptive vision. So this is all about the example. Means terrain mapping, path planning is an example of adaptive vision. Now, beside that, one other good example of ML which is happening in these autonomous cars is about means learning from human drivers. So this is a pretty good example of inverse reinforcement. So what is happening is means every of these autonomous cars are being driven by the expert drivers, and certainly what is happening is, so inverse learning is happening, inverse reinforcement learning is happening. So this car is actually learning from those human drivers. So that is what the thing. We had seen this learning, deep learning, and headlines and the news too. It's like this means nowadays we are having this news reporting, and the news are getting generated through machine learning approaches. It's getting done nowadays. We had a good example of news reporting by a good of the ML agent in Indian news media, like means we see it in G News and Aastak also. There the agent are there which are actually reading, and not only reading, rather the news is generated by these ML. So you have a huge information data sets, and certainly the news based on that is being generated. Then we have good examples of means face image detection, classification kind of problem. The deep belief nets are there for that. What we have, how it goes is like this means we have input images, and the information is in and the pixel level. How these images are actually means these deep networks are learned uh, through this input image and the labels associated with them at another end. So what happens here is means we have these pixels, and pixels these feature maps, and the higher layer means level feature maps are generated from these pixels, and then object parts are uh, uh, formalized, and then certainly we have this class label here. So this is how means the object means the model is trained with this input and the input label. with this intermediate feature engineering. And certainly if there are multiple classes, so then we have this input and the means at this layer and the multiple classes at another side of it. And certainly this model same model get trained for all these different classes objects. So that's the thing. Another good example is of scene labeling. We all know about this means image description, scene labeling kind of the problem means let's say we have this image and certainly we need to give caption to this image or some labels to this image. So we have good examples of it means where we have means ML and DL getting utilized. Another good example is this means so we have these partial face images, and certainly we have to actually means recreate the remaining partial pose of the face. So good of the deep inferencing models are there which are actually doing means this kind of thing means we can do this kind of thing. Another good example is of means speech recognition, automatic speech recognition. So what we have models like this where the feature extraction and the classification of those samples, voice samples is getting done, and then the next part is of decoding that voice samples into the text words and so on is done by the decoder, and then transducers and the language models actually recreate them into sentences. So these are the things means so you have an involvement of good involvement of these ML models here in this feature engineering as well as the classification part. Another good side of it is means same, or you can say the extended kind of application of those speech recognition. Here we see an speech technology agents like means we have Apple Siri, we have Google Now, we have Microsoft Cortana, we have and so Alexa from Amazon, and so what is happening therein? So this is what that machine learning on the voice signal processing with the NLP involved is getting done. Uh, that is what the thing. So these were the some of the good state of art examples and the applications means which are floating now all around of us. All right, so examples are all the way means more than that, and means there is no limited number. We have limitless applications where these are getting used. ML is getting used. But the thing will be means how that ML is actually doing the things. So then in that case, we shall understand that ML methodology and the ML methods. So how the things happens. So let's then look on means this ML algorithmic methodology you say, or ML methodology. How the data is actually is actually creating the machine learn. So so for that we have to then look on means different categories of the ML approaches which has been defined. So as we had already seen, that means and talked about it means ML is all about the data. So you have variation and the differences in the data available with you. Certainly the methodology you have to adapt will be different for you. So this is what the thing is. So the differences and the categories in the ML approaches are actually driven from the differences in the data we have for the application all around us. So there could be application where we have the data seen as an complete experience, meaning that we have the whole information, whole knowledge about it. Let's say we have the input and the output class level information associated. So if we have an experiences of the data in completeness, then the kind of approach we have to actually derive will be different compared to if we have an experience which is incomplete in nature. The kind of machine learning model we have to develop will be different. That is what the thing. So based on this fact, we have categories of these machine learning approaches. So very first of it is like means where the data is or the experiences is complete in nature. So we have the input data information along with the output, the desired output, or you say the output label of that input data. So for an example, let's say I have an image of an object. So alongside I also know that what is that object, so what is the class level of that object. So if I have a complete information, means I have an information like this, so it's a complete experience or means complete data. So then in that case, you will be having one category of the approaches for 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 learning. So that is actually called as a supervised learning approach. So in another case, we have, let's say I only have the object image, no label associated. Okay, what is this object? Certainly, then in that case, I will not be able to utilize the previous approaches, previous category of approaches. Then I have to look upon some another category. That is, we say that is an unsupervised category of learning. Then we have a semi-supervised kind of learning category, means methods, category of learning methods. So there in that this case, what we have is means we have the training data, uh, some portion of it is supervised, means it is complete, having the output levels with them, whereas remaining and other portion of the enormous data is not with the desired outputs. So if such is the case, then we can actually have a, a, a semi-supervised or a combined approach of supervised and unsupervised. Then we have the reinforcement kind of method. Let's say we doesn't have anything, neither a partial means experience or a full experience. So if such is the case, then we have to go with means a very different kind of approach. And that is the case for an example of, let's say we have to move in an unknown environment. So we doesn't have anything of it, neither a partial experience, not a full experience, neither a partial experience. Then in that case, we have to actually uh, means learn in real time. That is what the thing, learn with every step we are taking in that environment. A good example was that Mars rover, means if it is moving for first time, so that could be a good example of it. So if every step it is taking, it is learning from that, and then it will be helping for the remaining kind of movements for his movement. So that's the thing. Now, if we elaboratedly actually look on these, so however, I know that means everyone sitting here i- is knowing about them, and let's have a refresh of it. Probably there could be something where maybe if there's some confusion lies about understanding. So this will be a good time for actually removing out that confusion in this elaboration. So supervised learning, if I talk about, so is somewhat like this. As I already told, that means what is happening is means we have a complete experience available. The data is in complete format, means it is with input and output. So let's say how does a machine learn in this kind of learning approaches. So we have these samples, input samples. These are complete input samples, input experiences. So now this samples in, let's say this is an example of spam and auto spam of the email. So we have numerous of the email samples, suppose, all with their output labels like some are spam, some are not spam, or something like that. Then we will get them input to this machine learning model, and certainly based on this all these input experiences, this will get trained. And once it is trained, then it will be able to actually classify any new kind of email which for which the output label is not available. So then that is what the thing in case of supervised approach. So this is what the same thing written for that. So we can see it like this means, so how actually more elaborately it works is like this. So we have these input data alongside the labels. Now, so are or is this data directly being inputted to the machine learning algorithms, or is means some processing has to be done on it. So what is the thing is means these machine learning models are to are designed to take input now, but input has to be in what shape? This is very important. So is a raw input good for them, or some sort of means processing of that raw input is required for that. So certainly what is good to do is that we shall actually look on for the characteristic features which clearly differentiates alongside me these objects alongside these labels. So let's say if I am having two output classes or a three output classes, so all these means inputs. So we have to look on the prominent characteristics which actually differentiate one sample from other based on these classes, into these classes based on these characteristic features. So that is what the thing. So instead of a raw information, it is better to actually extract out those prominent characteristics. So this is what is called as feature. So these are nothing but characteristic features which we are extracting out of those input, and certainly that will make our machine learning approach more correct exactly. So what we do is we do the feature engineering. We apply those extracted features to the machine learning model, and certainly our model is getting trained based on it. Once it is trained, we can actually apply this new sample with the same process, and we can get an expected level of it. Now, but another important thing is thing to understand is uh, we have huge set of problems where we have complete experience available. Means the data is available like means input with class label. Now, but further we can have a division like this means out of all those problems which lies under the supervised learning category can then actually be seen as means there are some problem where the kind of output we expect is one type, whereas the another set of the problems the output expected is of another type. So based on this output expected in case of these different problems, these all problems which actually are expected to be solved through supervised learning approach can be divided into these two categories like classification and regression. Now let's understand this. So we as we had already told about, so everything the game is of the data. So the data the representation is somewhat like this. So the data samples are like this x comma y. Okay, so these are n samples like x1 y1 x2 y2 and so on. So this is your one experience x1 comma y1 or one sample data. So what is x and y? So x is your input information and y is an output level corresponding to it. Now, this input for any problem, or you can say the n for input for any data samples in any problem will always be remaining same. But the thing will be what is the kind of output expected. So it's like this means if the output is more categorical, then the problem we say is a classification problem. So it is somewhat like this. Given an x, y is, let's say our x is a image. Let's say our x is an image of an object. Now what is y for that? So y is a class level that, let's say, I mean, given an object image, the object is a class lies in the class cat, suppose, in an animal or a human or somewhat like this. So this y will be one of the label out of those given labels. So meaning that this is more categorical kind of an output. So if the problems are having categorical output in the data, then these are classification kind of the problems. Wherein another case where the y is not categorical, it is continuous in nature, then those problems will be called as the regression problems. And the good examples of such regression problems are the prediction problems like weather forecasting and so on. We will have the example of it. Now let's move ahead. So good example of it is like this classification. Let's say we have many flock of means we have a flock of cats and dogs, and out of those cats and dogs we have to we know the anything about me means we know about them means to which every of the individual cat or dog means to which category they lie, whether they are cat or dog. So how, based on the information associated with them, the best of the information could we can think of as like the shape of that, and the shape can be seen through the height, suppose, and their weight, suppose. Okay. So cat, the weight and height is the input information, and whether it is based on that, whether it is a cat or dog, so it's the output label. So that's a simple scenario. Like we can see it like this. So we have a data x. X is a, instead of a scalar, it's a vector. Vector of two scalars, that is weight and height. So x comprise weight and height, whereas y is a categorical output, that is either cat or dog. So y can only be one value, either cat or dog. So that's what the thing. Y will always be a scalar value in supervised learning methods or in any method type. Now the thing is, so what we suppose we want, what we want to do here is, so we want to actually means draw a classification boundary between these two classes. So we plot them, we plot these data, and then what we try to do is we try to draw a classification boundary which actually clearly classify any sample between these two classes. Suppose we got a new sample. Now we have to check. So new sample means new x. So then corresponding to this new x, we have to check whether it lies within a means a cat dog category or the dog category. So how we will be able to do this? So we will once we got a boundary, then we will plot that point, and to which side it will come, we will give that respective class to it. So that's a simple thing. So if point comes this side, we will say it's a cat category. If point comes this side, we will say the dog category. That's the simple story. So the trick or the challenge here is what? How to draw this distinction boundary, and that distinction boundary should be so accurate that it actually discriminates or distincts every individual sample of it. All 100% samples are clearly discriminated from the from the training data. So that is actually a challenge. So then based on it, we can think of different kind of these decision boundaries. Like let's say we can think of linear. If it is the linear doesn't work, we can think of polynomial kind of boundaries. We can think of so many means curves and so kind of boundaries. And based on it, we have so many different classification approaches. We will see it. So what are those different kind of classification approaches? So that's the thing, means we have different kind of classification approaches, like means we have k nearest neighbor, support vector machine, decision trees, random forest, and there are so many others. So these are a bit more popular. That's why I had noted them. K nearest neighbor, probably I know. So this is what the thing is. What we do here in k nearest neighbor is, so take we have to actually look for a novel sample and check for, if let's say it's a two class problem, so to which of the two classes does it belongs to. So what we do is we put means take it as a center on the 2D dispersion map, and then we draw a circle with nearest neighbors. So how many nearest neighbor we try to draw a circle means wherein uh, five nearest neighbor, suppose, so n nearest neighbor we actually have to take in the consideration. So what are those n nearest neighbors to it? So we consider those, and certainly these nearest neighbors could actually be from any of those class, could be of any of those class. So then we'll go for voting. So, those nearest neighbors, so max to which class the maximum of those belongs. So which of the class is having highest voting in those nearest neighbor? So we check out those and we give the label of the same to the no, new sample. That's a simple story about it. Now there will be a problem then how to decide upon K. So this K decision is actually one of the important thing here is we the best of the idea is that K shouldn't be less. If K will be less, then there will be more chances of error. So more high is a K, better will be the result, meaning that we will be able to accommodate all the training samples certainly. So as high is the case, we but if we increase the K, the complexity increases of the model. So then we try to do is means one of the good ways, let's say we take a square root of n, means n are the available samples, we take means any odd value of n, so it is good to decide with the help of that. So that those are the ideas. Then we have support vector machine. So what we have here in, we try to actually create this boundary in case of support vector machine. And how to decide upon this boundary? There could be many boundaries between two classes, which actually segregate two samples. But what will be the best boundary? So if I try to create a boundary, so I can have a boundary here, it's also here also. So there could be n different lines we can actually create, or infinite number of them, those lines which can be a boundary. Now, in this case, example, if I try to say, so if it is well discriminative with a linear discriminable function, then in that case there could be more than one discriminative boundary, and this boundary is called as hyperplane exactly. Now the thing is means which one is best. So this best is decided based on the support vectors. So these are the support. What are those support vectors? Support vectors are the nearest uh, samples from two different classes to the that discriminative boundary. Farthest, you can say exactly. Uh, so if I say this, so uh, so these are the support vectors, but actually so what which of the support vector will be the best actually? So the best support vectors will be having the maximum distance from this hyperplane, will be the best support vectors actually in this case. So we have to actually look on that. So this is the deciding factor. And then so on, we have the decision trees and the random forest kind of the approaches. In the decision tree, what we do is we actually look upon uh, means we have the input attributes, and we have to design means create a decision tree based on the attributes at the node. And what we have to do is so that based on that attribute, the whole sample uh, is to be divided, that's get divided into the two children trees of that at that node of that decision tree. So this is based on how we decide upon this. Let's say we have three attributes in the input. So which attribute is decided to be at the root, suppose. So this is decided based on means having any attribute, it divides into two legs of that decision tree with a low entropy and a high gain achieved. So that is what so entropy, a low entropy and a high gain is a deciding criteria there in case of the decision trees, and so on in the uh, random forest approaches. Now, if I move up to the regression algorithms, I actually have to skip those and go in fast, since there are so many things to discuss, and time again is limited. So regression, if someone feels to actually raise up a question, please can come up, or I can even go faster and look on for rest many information I have in my slides, later slides. So if you have any question, please come up, and if you feel that we can skip this and come. So or I'm going a bit faster, and certainly you can stop me to actually elaborate on the things. That will be better. So regression approach. So regression problems, not approach. The approach is supervised learning. The regression kind of problems. In I mean supervised learning and regression kind of problems. So what happens here is, so same we have the sample, complete experience x and y. So x is any kind of input vector, whereas y is a scalar value, but it is continuous in nature. That is what the thing in case of regression. So we have available past in data, history data, where with sample x and y, x comma y. So what we do here in this case is, so we actually plot them, so we get a distribution like this. Now the problem here in this is, means what we have to do is, for a given new x we have to actually calculate y. So what will be a y in that case for an oval sample x? So how to actually calculate this? So the approach is, means we have to actually fit this distribution by a curve or by a regression function. So this a function which actually fits this data is called as a regression function. So how we get this so simplest of this regression function could be a straight line. So how we get this straight line or this regression function is, so what we check upon is the distance of this function of any of these points with this function. So what we try to reduce is, we try to reduce the distance or this error. So this is what the thing is. So distance of this point from this function means is the error here at this point. So we try to reduce this, and the error function we take up is the least square kind of thing. Sorry, the square of the error. And what we do is, we do an approximation, least square kind of an approximation. So that is what the thing is done. So we try to go for a best fitting line. So once we get a best fitting line here, and then with any novel x we can actually generate y, calculate y. So this is a good example of it. So let's say this is area of the plots and the price correspondingly. So this is a plot for numerous data samples. Now for any new input, like means plot area, we can then calculate an estimated price for that plot area. So this is what the thing. Now the thing is, means we can well see here is that this regression function means this straight line as considered as a regression function is not fitting the whole distribution correctly. So then we can look for a more polynomial kind of functions and curve and the surfaces kind of functions for it. So these are the means different categories of the regression algorithms. Like linear regression, we have logistic regression is nothing but it's a staff function. It's you can say linearly discriminated staff function kind of thing. So not only for the regression problems, this logistic regression can also be used for the classification problem. Polynomial, then we have polynomial regression, we have stepwise regression, and in linear we have simple linear, multiple linear regression kind of things. Then we have a category of unsupervised learning. So the problem is somewhat like this in unsupervised learning is, means we have the data with only x, no y is there. So if such is the case, then we doesn't have any class level at all. We doesn't have any class at all to actually distribute them the samples in. So if we try to plot them, so they would randomly be plotted here on this plot, but we will not be knowing whether they are similar or dissimilar or anything or like that. Then in order to understand them well, what is a good approach? So good approach is clustering. So let's do a cluster. So let's divide all that distribution of samples into different clusters. Then it will be easy or good to actually understand those samples and the data. So this unsupervised learning is nothing but it's a clustering kind of problem. So how the actual problem here in this clustering kind of problems is, so how to decide upon the clusters. So let's say we have an input with two features. So then we can plot it on a 2D distribution map. Now the problem will be how to decide upon that these all available samples will have to be segregated in three clusters or four clusters or five clusters. So what will be this k actually? So we have various methods actually. We have k means algorithm and so how to decide upon this is, so this is, or these method, how does these method start? So we can randomly take up choose upon this value of k and check upon the distribution matrices like the covariance matrices of the clusters generated and in different cases of k, and the best you get. So what has to be done is, so the variance should be less and covariance should be high. So that is the good idea for this clustering. So that is approach for clustering, and then we have semi-supervised, where we have the data which is complete, means partially complete, partially incomplete. Then we can use these approaches like the example of this could be like this. Means let's say we have a photo archive. Some of the photos we have a label associated, means a caption to them, but rest of them are not having any caption. So we can think of a semi-supervised kind of approaches. Another good kind of category is means reinforcement. And what happens in this kind of learning is, means this is all about means learning in an unknown environment, a real time learning in an unknown environment. So how the real time learning will happen? So what is the basic methodology against it? So it's somewhat like this. So in let's say this is the environment, this is the agent has to take move in this environment. So it will take a move or it will make an action in this. Based on that action, what actually he experiences, that agent experiences, will be that feedback measured in terms of some rewards, positive or negative rewards, will be a learning to this agent. So this is what the thing. So let's say I have a model here. This will give a good explanation of it. So this agent takes an action AI, this environment. So this system, you say, or this agent enters into a different state with a different reward. So this is what the thing is. So it's an state space model. So with a in a different in any state with some reward value, this agent is getting trained. So and this reward could be positive or negative, somewhat like this. So whether means and this new state could be, you can say, endless also, or it could be like this. We can see some feedback, means you say a circular kind of means state space like this, means having some reward and action associated, means same kind of action associated, then we are reaching to a same state like that. So this is a state space kind of model, and this is what the thing. So the key thing behind this reinforcement learning is this reward and the action associated. So the actions means this agent learned from the action and the reward, what he is getting. Reward is nothing, what he is experiencing is the reward. So it could be a positive or the negative experience. The positive experience, so it's not typically binary, this positive or negative. So what value of positive is again added to it. So it can be clearly shown with this picture. Let's say this is an environment, this is the agent. So let's say it has to move. There are two possible move to it. So suppose this is one side or this is another side. Let's say if it moves this side, what he finds is it's a fire, it's dangerous for this. So what he get is a negative reward. So in this case, so this negative reward will be the training here, will be a part of the training, and certainly in next case, this negative reward corresponding to this state of the movement will actually be deciding factor for any other move uh, towards this kind of state actually. Another good examples of it, you all maximum of you might have played this kind of game, Mario. So it's a good example of reinforcement learning. This Mario actually is learning on every steps. So whether to jump or not, if there is a ditch in front or somewhat like that. So this is a good example of it. There are a few other examples like means credit assignment problem. Yes, that is a good thing. So that's a reinforcement is happening there in credit assignment. Game playing is there. The robot in a maze is another good example. Balancing a pole on your hand is another good example of it. So what is happening is you we do a reinforcement when we balance. So whether to move with what degree we have to move in what direction our hand, so that this pole remains balanced. So that is what the thing is, reinforcement happening. As I told you in one of the previous example means their autonomous cars, the same kind of thing means those expert drivers are intended from there. The car model is learning the things. Same is the example here. This helicopter means what is happening here is this inverse reinforcement is happening here in with this. So in nutshell, if we try to see, so we have hundreds of new algorithms coming up every years in this domain, and certainly they have or they can be categorized into some specific categories like this. We have a good summary of it. Now, if we try to understand any ML algorithm, so there the three basic component of any ML algorithm. So very first thing is the representation, function representation of the approach. So this function representation could be like this means a linear regression function is a, so a linear function there defined as a regression function. So that is a function representation. Now, second important is element a component is the optimization. So then we have to actually have a optimization function. Optimization for what? So in every step of the training, in every step of training means for every for every sample applied for training on that algorithm, what is the error we are getting, and every step of that training, what we have to have is that we have to reduce that error. So how that reduction, the process of reduction in the error will happen is actually the process of optimization. So we have like this means uh, gradient descent approaches kind of the thing are there. So where there are various optimization approaches are there. Then is the evaluation. So let's say we are done with the whole training process, then we will check upon or evaluate upon the model how correct the outputs are there. Then once the evaluation done is done, the we had evaluated it on various matrices like accuracy, precision, recall, and entropy or gain or somewhat like that. Then we will have the option and chance to actually uh, do a further step of training for further improvement. So that is what the thing. So these are the three important component of any ML algorithm. So this is a good summary of it. So where we have various kinds of these functions in ML approaches, like numerical functions are there, like linear regression. We have support vector machines, neural network. It's again what their numerical functions are there. Then we have some symbolic functions also, like in case of decision trees, propositional logics and predicate logics. So there is nothing like means numerical in there, and so what we have is means these are more non-parametric approaches. And then we have instance based function. The good example was that k nearest neighbor. So there is nothing like numerical in there. So it's more instance based. So So we actually are looking on those instances and the samples. Then we have probabilistic models like naive Bayes, so they works on probability, and the Bayesian networks is there. The hidden Markov model is there. Good set of optimizers are a gradient descent. We actually see in all numerical functions. We have dynamic programming approaches is and decision trees and all those random forests and the HMM kind of learning. Same in divide and conquer approaches. We actually have this kind of optimizer and decision trees kind of thing. We have evolutionary computing. Invariably can be utilized in various different functions, function representation. Then we have evaluation matrices like accuracy, precision, recall, and so many. Means so these are the evaluation parameters which decides upon whether to stop for the machine training or not. That's the thing. So all are important. All have got the good utilization, but rest of others, the neural network has got good importance, and the reason being it is having an immense level of the or the high end non-linearity exactly. So when we say machine learning is seen to be good when we add a higher level of non-linearity to it. And so the neural network are a good example of it. So let's talk about this. If anyone is having something to put, please can come up. So it's going very monotonous, one-sided only. So if you please have something to, yes, no, shall I carry on?
Yes, sir, you may.
All right,
It's going good till now.
all right. So I'll try to have focus on some important points here only, and talking about these artificial neural networks. So going faster. So artificial neural network, these are motivated from human brain networks that is we all know about. So what is there in the biological neurons which actually make it similar to the artificial neurons? So as we say that it's motivated from that. So biological neurons somewhat look like this. We have a cell body, inside that we have a nucleus, and what is it? The cell is this nucleus is taking input from other neurons through these dendrites. So input is coming from to the nucleus through these dendrites exactly. So input impulses are coming from there. So same way, this artificial neuron is created like this. So why is that a nucleus and the input impulses are coming from these x1, x2, x3 input nodes? And the important thing is means every different dendrites have their own contribution to the input impulses. So is being decided as the weights in case of artificial neurons. So w1, w2, w3. Now, if we try to see is this, so any artificial neural network is well specified through these three important components. So one is neural model. So how we are we are designing that one single neuron is one important thing. So meaning that we'll see the structure. So that what will be the activation function at the nucleus. That is why how this y is decided. What is the function y is equal to f is what is this f here, and how many inputs are coming to it. So this is all about the one neuron structure. Then second thing is the architecture. Let's say if we are using many number of the neurons in our network, then how that network look like. So how many layers, how many neurons in every layer, and the weights associated, and so on. That's all about the architecture. And then if what is the learning algorithm? So how this network, once let's say we had created a network, how this learning will happen in this network. So what will be that method of learning, algorithm for learning? So that is the third important thing. So let's go with this. Hope everyone is knowing it. I know it, but you can get a bit more clarity, I think, from here. So this is what a single neuron network. This is also called as a perceptron. So what we have is we this is your nucleus. So here what we get is this nucleus get input from this input impulses or the inputs here. So these all inputs are numerical inputs in case of neural networks. So here what we get is a weight. So all are having the contribution. So what we get is this is the weighted sum. So here this input is seen as a weighted sum of all these input input samples, input scalar values, you can say. So now this weighted sum, now that we apply a function on this weighted sum, so this f is, so this weighted sum here, this input seen in terms of this weighted sum is responsible for activating this neuron. So activating this neuron, so we have a function decided for that activation of this neuron, and this is nothing but f. So f is a function of this v, and v is nothing but this weighted sum. However, there is one more term added here is b. So this weighted sum plus b. So what is this b? B is a bias. There is a very important function of this b. So we'll see it here. Before moving to that, let's see this. So how do we calculate the output? So we have this x. It's a vector. So we have two scalar values x1, x2, and correspondingly these weights like w1, w2. So weighted sum is this w1 x1 plus w2 x2, and so on. This we get this weighted sum here, suppose, and then we apply this activation function. Suppose the activation function here is a simple, you can say a staff function. Okay, so staff function means, let's say if this weighted sum is less than 0.5, we make it y is 0. If it is greater than 0.5, we say that y is 1. So this is how we calculate, and correspondingly for this x1 y1, we decide upon this what will be our y. So this is how we calculate. All right, now we were talking about this bias. What is this? Why this bias is important? Is important. What is the importance of this? So exactly this bias. What is this bias doing? Let's see this function. V is so yes. What is this V? So V is this summation of Wxy Wjy xj plus B. So this is nothing but we can see it as a function of a means a line actually. Take a line on a two coordinate plane actually. So now this, what is this? So V output will be depending on this X as well as what will be the role of this B here. So B is actually doing what? Let's say if there is no B. So what do you think? If X gets 0, so you can if there is no B, if let's say we want a 0 output. So if X is 0, then only this V could be 0 or Y could be 0. So if we want output Y, even if some non-zero output, even if this X is 0, then we have to have this another term. So what we have to do is, this is what this you can say is acting as a y-intercept here. What it is doing, it is transforming this function to one side of this origin. So this is what the thing. So this is why this is important. So let's say if in any case this x becomes 0, so this neuron will not be activated at all. So what we have to do is, let's say we want, or other way, we let's say we want a non or a 0 output with a non-zero x. So suppose this is the thing. So how to get it? So in any of this case, we have to have this bias. A good example is here. So suppose this is the case, we have one input x and this is weight, and here we have a sigmoid function. So as an activation function. So what we get is, so with input 0, so with all these inputs here less than 0 till here, what we are getting this, we are getting this output as means means 0 here, and then it is changing to means any positive y. So exactly what is happening is, so we can get any output with any input x, but let's say if we are talking of x, I mean this output y to be 0. So how can we get this output y is 0? Okay, with any with some x. So x, this can only be in case of x equal to 0. Then we can get this y. So if this x is 0, then only we can in this situation we can get this output uh, uh, 0. But let's say if I want this output to be 0 when means on non-zero x. So how to get it? So it's like this. Means I'm here. Okay. So on this non-zero, so I want x this. This is here. Output. I'm sorry. You have 0. This is 0. This is 0. Output is this 0. So when this output is coming 0, this output is coming 0 on uh, x less than 0.
When x is negative, I guess.
When x is negative, right? Uh,
As x turns out to be positive, then y
yes.
becomes positive.
So what is happening is means in this case you can't get x means the output to be 0 when x is less than 0. That is what the thing is. So if I want for a positive x, I want an output 0, suppose. So how to get it? So it will not be at all possible with this. So what I have to do is I need to actually means if I shift this function here this side, so then it is possible with x greater than 0, I can get output 0. That's the thing. So means I need to actually shift this function towards x side. So how can I do this? So then in that case, what I have to do is I have to add that constant buys here. Okay, by which I can actually shift it to any of these direction. So that is what the thing. So I actually add a bias here, and I can actually then shift it to means means x direction positive side, and I can actually get any other means x to get an output 0. So this is what an important thing about means the requirement of bias. So it actually transposes or transforms this the activation function in y axis actually. Now,
Sir, I like to ask one thing.
yes.
Like at what point we should start with bias? Like we should start
I we are having a
implementing
yes, we are having a
implementing
yes, we are having an example next.
right, right.
uh,
And
so
can I join one more question?
yes.
What is the criteria for selecting the activation function?
We have all these there in the upcoming slides. Don't
Okay,
worry. Okay.
okay.
So that is what the so the question was how to decide upon this bias. What should be the good value of bias? So it's very clear that b can't be 0. It can be either positive or negative. That's what. Now, b, shall it be positive or shall it be negative? So then we have to look on. So what is the best bias? Whether it should be positive bias is good or negative bias is good. So now with this example, let's see this. So this is a realizing a or function with the neural network, a perceptron. So we have this w so two input perceptron. We have weights w1 w2, and we have this means your v equal to this plus b. This is your bias stick. Now what we have to implement is this function. This is the function with these possible inputs of a and b and this or. So for 0 0, let's check out for 0 0. So if x 1 x2 are 0 0, certainly this output function will be the function of b. Now for this and suppose the activation function is a step function that previously we had seen, means if the this v goes to be less than zero point 0.5, we say it is 0, output is 0. If v goes then greater equal to zero point 0.5, output is 1. So now in this case, this what we have is for very first case we get this as v equal to b. Now what we want, this should be what should be the value of this b so that I get an output of this step function 0, meaning that this b should be less than zero point 0.5. B should be less than zero point 0.5. So in this case, means if I take this, I can't take this as greater than zero point 0.5, means I can take it 0. So better is let's go with, means I can't go with 1 or 0. I have, let's say I go with -1. So let's take this, make it -1. What it will do is I make it -1. Then what will happen? It will be less than zero point 0.5, and the output will come out to be 0. So very first case is clear. Now with this bias decided -1 with this very first case, whether it satisfies the rest of the cases or not. So it is here. So let's use for 0, 1. So the 0 and 1, we replace it here. We put bias as -1. Now W2 comes to uh, now based on this output, what we have to do is means the output was in the second case the output, so actually these outputs are wrong for OR. This has to be 0, 0, 1. So in combination of 0, 1 input, this has to be 0. Here it is taken correct. So this this first case with input 0, 1, the output is 0. So W2, then we can calculate W2 as 1. Taking third case, there's 1, 0 combination, the output again should be 0. This is actually by mistake written wrong. So now we replace it here, 1, 0. Bias is taken as -1. This becomes 0, and this is W1 -1. And this third case, again, the output has to be 0. Then based on this, we calculate W1 as 1. So what we get is we all get the values of W1, W2, and we already have decided bias. Now let's take the last case. This shall also be satisfied. With A and B as 1, 1, this output should be 1. Now replace in this last case, whether it satisfies or not. So 1 into 1, 1 into 1 means all these weights were 1, 1. Input are again 1, 1. So 1 into 1, 1 into 1, and B is -1. So what we get is 2 minus 1, and then output comes to be 1. So this is what this value is, FV. So this is the, now we have to apply this step function on it. So since it is greater than 0.5, so what will be the output? So Y will be 1, and that is what the output is expected here as 1. So meaning that this is the way we can actually calculate upon the weights, and this was a very random kind of example. So now, so as this example gives a good case of, means deciding upon B, that negative B as we had taken here. Again, it's not a generally means it can't be a generic statement with this example. But what is good to be taken as bias? So it is preferred to have negative bias. So if we have positive bias, what we get is that bias starts adding up. So once it starts adding up, what happens is it actually results into the error, means a very positive error exactly, and positive means increasing positive error. So then it reduces the rate of that gradient descent actually approaching towards that minimum error or zero error. So it is good to actually have, in order to have a good pace in the training, it is actually good to have the negative kind of bias. Hope that is okay for you. Is that?
Yes, sir. Yes, sir.
Uh, Remaining other things like me deciding upon the activation function, we have a few other slides for that. So now this learning process of the neural network, how it goes. So it's somewhat like this. What we do is we take a model, we compute output with some random weights assigned. We check for the output and we compare it with the actual output. Then if there is a difference, based on that we actually adjust weight, and this cycle goes on. Once we find that, means desired output is actually is actually similar to the actual output or very nearer to the output, then we can decide upon stopping this training. That so there could be the two stopping criterias, like one is when this error get reduced to very small value and there is no fair chance of further reduction of the error, or the second is the number of iterations, so how of or the epochs of the training we decide upon. So if your training epoch is taking so much time, then you have to limit on the number of epochs of your training. So that is another criteria for stopping. Now let's see this. So how this weight is adjusted. So how to get a new weight, and the weights are updated. So this is what the thing is. So weights are updated based on the error we find in that step. So this is d minus y is d is the d is the desirable output, y is actual output. So this is a difference is nothing but this is a delta error, and now we multiply it by x. Now, how we get this? This delta error multiplied by x is actually your delta W. So this is based on what? So this is based on uh, the error we take was the squared error, mean square error. So squared error, why we take the square error? Squared error. So squared error means that is for the region, means if we do not take a squared error, so what happens is sometime means the positive or negative errors, if you subtract them, one side we have positive error, another side we have negative error, and if we subtract them, that error gets added. So it's not actually good to go with simple means delta difference. Rather, it is good to go for the square of the error, absolute error, or the squared of the error. So our error function or the loss function happens to be square of the error. And once we do it, and in the gradient descent, so for error to reduce or to become zero, what we do, we actually do the first differential zero of it. We take the first differential and we try to make it zero. So so this is nothing but this d minus y square, do take the differential of it. So what it will come to, 2 into d minus y into the del d by del x. So this is what the thing. So from there it comes to be d minus y into this new x. Okay, and this is the eta. Eta is the learning rate. So this is how we get in case of means if we have an step function, and this is step activation function, and we have the means in case of classification we use the squared mean squared error as the error function. So the weight, this delta W will come out to be this. So d minus y into x previous into eta is the learning rate. So eta is added extra to this to actually means what you say, to have a control on this learning speed. So actually this is your delta error into x, and this is your delta W. So this delta W is added with W, previous W, and you get a new W. And this is how the weights are updated. That was in a case of means this was in a case means this delta W was this value in when you have a step activation function. Let's say the activation function is sigmoid. So what happens to this? So this was the case. Your delta W was in case of here. This is the example. Sorry, this is the case of means when of the delta W where the your activation function is a step function. Now, so this is your delta error, your x multiplied by, so this delta error is nothing but d minus y or td minus od. So this is td minus od into x into this new eta. So this is the delta W for step function. Let's say this step function, this activation function is changed to this sigmoid. 1 by 1 1 plus e to the power minus x. So what happens in this case? So what will happen here is, so instead of this, uh, we have this Dale term on x. So when this Dale term on x is replaced by Dale term on is sigma x. So what will happen is, so it will this will replace this sigma x 1 minus sigma x. So actually what is happening is, Dale term on x in previous case gives you x, sorry, x square. Dale term on x square give you x, while here what it is having is Dale term on sigma x. So what will this give is, sigma x, Dale of sigma x by dx is nothing but sigma x 1 minus sigma x. So what will be this value? This value will be nothing but this will be OD into 1 minus OD. So this is the new term which will be added. So this sigma x is nothing but OD, and Dale of sigma x by Dale x will be nothing but sigma this OD into 1 minus OD. This is what the thing. So new term means this delta W in case of sigmoid function, sigmoid activation function will be this instead of this. Are you getting it? So this is how this training happens. So for multi-layer perceptron, we can similarly actually have this calculation of error function and the weight subdation. And this is nothing but called as a back propagation. So what you do is, means actually we give input from this side and we start calculating error from this side and from the back side. That's why this training is actually called as a back propagation. Now, a few important facts to actually understand about the neural network is, what is important in the neural network. Let's say we created a network. Now, how to actually get a better output with those neural networks? So, how to decide upon those different elements of those neural networks so that we can get best of the evaluation output. So, very first thing is features. So, whether are we giving a very raw input or more featured input to the neural network is one important thing to actually improve your result. So let's say how better features you are providing to the network. So it's like this, means you have the input layer, you provide an input to that. Now let's say let's take with an example like this. Let's say we are talking of this spam detection kind of problem. So what is the input you are providing to the network? So are you providing the body of the email directly as an input? So your output in this case will be very different. Compared to this, if you are also considering the metadata in the mail, of the mail as an input, then your output will be different. So actually you have to actually look on the best features in the mail which decides upon this classification outcome. So here in this case, let's say we have given an example of this email header, the email structure, the language, the frequency of a specific terms. If we actually extract out these features, the grammatical correctness of text, these features prehand, and then apply it to the spam, this our classification model, this ANN suppose, then it will your model will be working in a different way. Exactly, will be giving more good result. For one more good example of is, let's say we are talking of uh, object classification and image inputs. Okay, so one of the way out could be we directly give the image as an input. Means let's say we have an input in image as 28 cross 28, so it comes out to be 78 784 pixels. So one of the simple way could be, let's say we give input these 784 pixels to the network, so that network will be trained, it will be giving you some output, but probably it will not be very good kind of accurate results coming out to be. Your model will not be that precise. Okay. Compared to that, what we can do is we can look out for some features from that, and then we actually give those features as an input to it. For an example, if we say, so we can, let's say we are talking of an object there in an image. So we if we can process that image, 28 cross 28 image, for some features like uh, the coordinate and coordinate pixels of that object, the boundaries, uh, the circulating box, and the radius features and size, shape kind of thing, or texture kind of the features. So if we actually improve those features, means extract out features and which are more relevant information compared to that raw information, and give that input to the ANN, then your model will be working very good. And that is what we have actually seen in case of the convolutional neural network. What is the typical ANN is the last part of that neural network. Beforehand, what is happening is the feature extraction. So that is automatically done there. Here, in case, let's say we are doing our own self, then we extract them and then we apply it to the ANN, and we get more good results. So features, the kind of features we are using, or if feature engineering we are doing, is an important job. Then second is the activation function. So there are so many activation functions, starting with, let's say, step function is not a very good function. So then we know about this sigmoid. So sigmoid is one of the popular function which was typically getting used earlier days. Okay. So now let's look on the pros and cons of the sigmoid. So sigmoid is well and good until we have very large z. But let's say z goes on. What is this z? Z is nothing but this wt, this weighted sum plus v. So if this weighted sum plus v, this z, b, this is z. So if this z is coming out to be large, then there is no problem. Okay. Then the sigma z will almost be nearer to 1, and there is no problem that the neuron will be activated correctly and it will be contributing to the training part. But let's say this, if this z goes on to smaller value, what will this happen is, once z goes to be smaller, this comes to so this e to the power minus z will be larger, and this inverse of this will be, means, very small. So, and this will lead, so when it reaches nearer to zero, what will happen is this will deactivate, this will kill the gradient, and it will lead to the non-activationness of the neuron. And certainly then we will not be able to reach out to the means we can't ever reach up to the zero kind of the loss. Okay. So that is what the case. Then it's a compromise model. This will always be compromise model. So what we can do is, so sigmoid. So the in this case of sigmoid activation function, the neurons, means they get saturated. So what? How can we remove this problem? So if actually we, instead of this, the function, means uh, means it's traveling between 0 and 1. If we try to actually manipulate this function, if we make this higher, the lower bound to be minus 1 against this 0, meaning that if we turn out this function to 10h, then certainly this problem of saturation will actually get reduced. So then we have got a new good variant, or alternative variant of this sigmoid function as the tanh function. So tanh, actually, then the bounds of the tanh are minus 1 and 1. Then in that case, this zero issue will get reduced, and the problem will get. But then again, tanh is getting somewhere popularly used, but again there is some problem with the tanh, is that it is complex. So it is complex to actually calculate these e minus z and this inverse of e minus z kind of this operation. So that's why these are the expensive operation, and they require more kind of CPU operations. So that's why, means, it's not good to actually use those sigmoid as well as 10h kind of the activation. Now what is good then? So then new alternative come up was the ReLU function. So these are nothing but rectilinear units. So what we have a series of such rectilinear units which actually work as a activation function. Now, what is the problem with this ReLU is, so we can well see from this graph. So what is happening is, for all values of x less than 0, the output is coming out to be 0. So you only get the non-zero output for positive inputs, positive Z. So then in that case, negative all zero and non-zero means non-positive all zero and the negative Z, you get a zero uh, output. So then what is happening here is means then in that case again you have very good number of the non-functional or the non-activated neuron problem is coming out there. So, and it leads to this gradient vanishing problem. Now, how can we reduce this? So if we actually this zero issue can be reduced by means if we gave a leak here at this negative side. So instead of making this very much straight here, all means zero output for all negative values. What we provide is we give a leak here. That is, it will not be exact zero, but rather it will be some small negative output will be here for all these negative inputs. So this leak will actually reduce the problem of the gradient descent means vanishing gradient actually.
So
Yes.
when we will be running our program or when we will be training our model, what indicators will be there that will reflect that this gradient is vanishing?
See, what happens is this is so if your training after some epoch is not means your error is not getting reduced.
Okay.
So this is what the thing is means you had stuck into the means local minimum kind of thing, and further the gradient is not reducing towards the zero value.
Mhm.
So that is what an issue. So
Okay.
the results had been seen by changing leaky reloom, and then the improvement had been seen.
Right, sir.
Then the next is the softmax activation. So what is this for? This is for actually what happens is in case of ANN, the output layer, the V. So we have n classes at the output layer. So all those output at the output layer, the value we get are the continuous values, or those are the probability values, posterior probability values. So instead of that, if we want to uh, actually hard max them, so it's like this means what we get is we get these posterior probability values. So probability, let's say the probability of that particular class of an object may belongs to. So let's say for this class it is giving to be 0.84. So this is a probability it is giving. It's not giving us 100%. So there could also be some probability for other classes for that object to belongs to. So then in that case, let's say we know that the one is having a highest probability, the class which is having a highest probability, the object belongs to that only. So then in that case, we can do a hard max. So actually this is for that purpose. So this layer, this softmax function is to actually do this what we say normalization and the hard maxing. So the softmaxing is done for that. And we if we talk about the loss function, so loss function in case of regression, we as already talked about, this is a means squared error, mean squared error. Whereas if we talk about this classification, we have this entropy function as a loss function. And this is the gradient descent. We can see it here. So what happens is, so this is the gradient descent we actually applied to. So what will happen if we do not apply this gradient descent? So we have to then trace out this whole curve in order to reach to this zero or the final value. So what in order to speed, so if we do this, so you can't at all means train any network means giving that much time. So this is what we try to do is we try to skip some. So what, so actually the thing is how fast we can trace this curve. This is a loss function curve. So how fast we can trace is the actually objective is the of the optimizer. So so the best of the optimize, one of the good optimizer is this calculating the gradient. So from here if we calculate the gradient, so we can reach up to this means this we can draw a line with slope, this djw by dw, so it will actually hit here. So the next point of uh, means calculating delta w will be this instead of a very next point this. So if we do this, but if we actually do this gradient calculation, we are able to trace this curve error curve faster exactly. That is what the thing. And the problem of that gradient vanishing was this, that if in any case without reaching here, from here to here we actually come up to this side of the curve. So what happen in this case, what would happen, what will happen is that we will keep on jumping from this side to this side, but will not be reaching that global minimum or the zero value. So it's not zero actually here, it's a global minimum here. So that is vanishing of the gradient. So gradient will not be changing, and we will be keep on sitting at one place. Is that correct?
Right, sir. Very nice.
All right. So now we working out these, we had seen means training the neural network, we had come up with few good kind of the challenges. And some of these challenges are, so one of the very first challenges underfitting of the model. So how does it happen is, so it's actually, let's say what happens is, we have the data, but data again was not very large. And what we do is we actually do train our model with that smaller data. So what happened, and then our function was again very simple. So if we have a very simple function, what it will do is, it will actually give us a classification boundary like this. So this is what the thing is. So if this is a very simple function, it will be giving a classification boundary like this. So meaning that it will not be very correctly fitting whole of these me samples of these two classes. So this is what the problem here. So this is a problem of underfitting exactly. Compared to that, what is expected is that all the boundary should come out to be in a way that maximum of the sample should be clearly discriminated. So if we try to come up here, so this is a more appropriate kind of a fitting. So instead of a linear kind of function, we can look on some curve kind of a function, which will give you more appropriate fitting, meaning that what we can do is, we can look for a more more complex function, we can say. More complex function means, here in this case the more complex function is this instead of a linear, we had taken this curve. Now compared to this means, even if here what we are finding is, there are 2 points, taking this example, there are 2 points of this plus class are coming in this class. So again means it's not 100% accurate, the precision is not 100%. Then in that case, what is, if someone is actually sitting for this only, that I have to make it 100%, then what can be done is, the same model is trained multiple times with the same data. Now what happens in this case is, if you do keep training it with the same data multiple times, if your model is not big, if your model is same smaller mlp, if your data is same smaller size, however you can think of your means, your data is having many, one of the cases, if your data is having many attributes, that could also be one case. So if you use many attribute, means the data with multiple attributes, then also, or if you keep on retraining with the same data on that simple model, then what will happen is, it can come up to this situation, and this is a overfitting kind of a situation. Then it will not be, what will happen is, it will not be able to classify a very novel sample which might come. So this is a overfitting situation, or you can say it's a cramming situation, it's a memorization problem kind of thing. uh, Same if I try to see in case of regression problems, so it is somewhat like this. So this is a very true function. It's a not this was the overfitting situation. So if we try to cover all the points, then what we are doing is, we are overfitting that distribution. and this is a good fit. That linear was not a good fit, that was underfit. If we were covering all the points, it was overfit. And however, this is a good fit with low bias and low variance. Now, actually, the thing is, if we try to see in underfitting, what is happening is the training data is less. That is all the okay me in both the cases. But what is happening is, sorry, yes, in underfitting the data is very less. We have that is what it is resulting in a low accuracy. Where while in case of overfitting, what is happening is actually training data is not very large. You say this last term here is not correctly written. What happens is the same training data is utilized multiple times for the training, or the the attributes in the training data are increased. So what do I mean with the attribute is I have increased the feature vector size or the feature size exactly. So let's say previously I was having only two features, I was using only two features, I did the training with the same data, so it results in underfitting. Against that, I actually then in next time what I do is I do training with some 100 feature randomly, I mean, or anonymously. I actually do some sort of feature engineering and extract out 100 number of features out of one sample, and then do the training on it. What will it then result is? Then it will result in the overfitting. Then meaning what means, then any new sample coming up, it might not be there, that that model is classifying it as correct. So that is what the thing. This happens to be a memorization problem. So how then can this be resolved? So the the solution to these, this was what the place where we got stuck with the ML kind of approaches. Then they come up with the idea that let's actually do increase or means move up from the MLP to the large models or the deeper models. So MLP were restricted to the 3 layer, 4 layer, or only this much kind of the size. Then we actually decided upon increasing that, these making our model more deeper. So this is an idea, means we increase the size of the network. And if we try to see in the means the these deep neural networks, so now we had got so many different proposals floating in the research world for these deep networks. Like means if we talk about, so deep feed forward network is very prevalent kind of example, that same MLP is extended for many layers. Then we have deep convolutional neural network. So we have fully connection ANN means added with a convolutional network. What it is giving is it is actually working on the features, more prominent features, and doing that classification job. Then we have auto encoders kind of the thing. So what it is doing is means it's transforming the input into different dimension, and then doing out the classification or the generative modeling kind of work. Then we have LSTM kind of the models where we have so previously all these previous models, they were actually restricted with uh, the you can say the data which is not a timeline data. So against that, if I want to work on some timeline data, means it's an activity kind of thing, or it's an it's a timeline event kind of thing. So I want to do machine learning on it. So then I have to have some history.
Sir,
Means yes, yes, stop.
conclude, sir.
It's conclude. I mean, is the almost last or second last slide.
Okay, sir.
So then we have to look on the history actually. So let's say if I'm talking of the event, or I want to model activity exactly. So I have to have a relation with the previous instances or the frames associated. So in that case, I want to have a history, or the means there should be a scope of having history in my model. That is that it shall able to have a retain that through a memory. So LSTM are the or the recurrent networks are the examples of it. Then we have GAN. GAN are the good examples in the generative modeling space. So then we have so many new models, and now it's last. Thank you. I was also looking on that I could have done with some examples means program also. So if you can means permit me for 5 more minutes, then I can go with those few programming examples if you don't mind.
Okay, sir, no problem.
So if the participants wishes, so I will just like to show a few examples. I don't know, means you might also be aware of programming these ML models, uh, and one of the good kind of program means the platform to work out this is the Google Colab. So that it provides you the free computational resources to actually train your ML models. So if I move on to that, I have here. So my collab window is okay, is visible.
Visible, sir.
Uh, so just in a very faster go, I'll let you know about it. So this is actually this is an example program for classifying the numbers. So numerals 0 to 9. So, however, these images, so this is based on the image set. So we don't have, rather, there is a repository here available in the collab. It's named as Amnest. And this Amnest is a data set of those numerals, numbers, so 0 to 9. So there are thousands of images of these numbers there in the Amnest repository here. So what we do here is, so what we will try to do is we will actually try to load that data set from Amnest repository here in our, and we will try to create the objects for training samples and the testing samples. And then we will try to see here how to resize these vectors, the training sample vectors and the test sample vectors, and then how to actually create a model. So and how the those model parameters will be assigned to it, and we will see the prediction or the classification output of this. So exactly what we are doing here is, so this is so we are actually using three libraries here. Where one is NumPy, one is Matplotlib, one is Keras. Keras is actually a higher abstraction library of the TensorFlow. So Keras supports much of higher abstraction functions here in ML and DL. So Keras, we have the dataset package. We import Amnest dataset from there. From same Keras, we actually import the sequential model. Sequential model is here. The sequential is a very basic model defined here in this Keras library. So see, it's like means a very basic MLP structure, ANN structure. Then the architecture of the layer is defined in dense. So we have to import this dense also from this Keras library. And then we have this optimizer. We are importing like RMS prop, mean square prop. And beside that, we had already means imported this matplotlib from for plotting those outputs, image outputs, and this is all. Let's go with this. So what is done here in this is, so we here this is the line which is doing actually loading that Amnest data set. So this is amnest.load data is doing this. We are loading this in, and two we had created two vector objects for training and the test data. So this is X train and Y train matrices vectors, and this is X text and Y test vector. So what's the size of this X train and Y train? We will see it. We can run it and see it. We can find it. So actually, this X train will is having what? Is having the image information. So image is 28 cross 28, and there are some 60,000 samples of such images. So 28 cross 28 cross means, so it's a three-dimensional vector actually, X train. And sorry, yes, Y train is a one-dimension vector, so it's only having an output label. Same way as the X test and Y test. This size of X train means the total number of sample and training is 60,000, testing is 10,000, and then let's try to run it. So in means small blocks of the code also it facilitates running. So if we run it, what we get is this. So this is here. This is simply giving uh, that size actually. Okay. If we next see this, hold on. Let me. What's happening?
So probably you need to run the first block first, yeah.
Hold on. This showing error. Yes. It's okay. So this is what it's showing means it has downloaded that much data, and then once it is done, here what is so it's showing the size actually. Take a training and testing sample size. Uh, we had normalized the values there in this range. So actually, those samples were the grayscale samples. So having the intensities going from 0 to 255, what we had made is we had made them black and white images. So normalized to 0, 1, all pixel values. Then this is our model. So what we had created this model, this is a sequential model having now how many layers we had decided. We had decided 4 layers here. First layer is this what we give here is the size of the layer, means that is how many number of neurons we are putting in this layer. What is the activation function in each layer we give, and this is not very mandatory. This is optional thing, and we can even write or skip that. This input shape. So input shape is 28 cross 28 means 78 4 number of pixels are there. So that is what the size. So, and the last layer is the softmax layer. That is what is the last layer of the at the output. So how many classes we have? We have 10 classes. So this we give this number of classes in the output. So a num classes is we have defined upside as 10. And let's see the model summary if we run it. So this is what the model summary. These many layers, these many neurons in each layer, and these many number of the parameters are there. So this all gives that. Now, once we do it, then we have to actually define the loss function, optimizer function, and the matrix. So in the compilation, and then we have to actually with these parameters we have to fit the model. So fit the model means then in this model fit function we have to give the training samples X train, Y train. We have to decide the batch size. Here the batch size we had upside defined as 128, epochs we had defined as 2. So let's run this and we'll show the training process. So this is the very first epoch, and then is the next epoch. So 2 times the whole number of samples are trained, means the model is trained 2 times on same samples. So now we can see here it's giving us in very first iteration the net accuracy was coming up to 0.37, loss 2.0. In the next epoch the accuracy reach up to 0.83, meaning the 83%. So if we try it one more time, certainly the accuracy might improve actually. So let's do it once more. So we can see this from 83% now it has increased to 92, 90, and then 92. So probably in how many epochs we can reach up to 100%, it's not very clear. So then let's go for, once this model is trained, now we can actually test it for some sample. So here this is, we had actually taken this one sample X test, and uh, this is 4 colon 5 is the particular means the space of that object. The So let's say this. So this was 4 actually. So 4 and see the classes here. The prediction, it's giving for all 10 classes. Output is giving for all 10 classes. Now see for which class it is giving the highest probability. So from here we can see this. Highest probability is coming out to be this one, and this is actually this 0, 1, 2, 3, 4, class 4. So that is what the thing. So it this is classified as value or digit 4. So this is what the thing. Just in a minute I will show you run this another example. This is an example from Cipher 10 dataset. This is having again 10 classes of different other objects, 10 random objects. Let's see this. The same ANN is defined here. Then we load this data. So these are the readily available data set there in this collab. Then we defined this function, and there is a model summary. The same kind of function we had defined. Here what we had done, this is a larger network actually with these many number of the neurons, 128 neurons in each. Then this is we had doing the fitting of the model. Again 2 epochs. Second epoch 30%. It can further be increased. Let's say one more times we do it. No. So 36%. Let's say try for the prediction. So what it is showing. So this is here. Now see what it is giving. So this is giving us the prediction for this class. Maximum probability is maximum. See, since the accuracy was only 36%, so probability haven't gone very high. So maximum probability even has gone to 27% only. Means 0.27 only. So that this is what the region. So none of the class is clearly means defining this. If we further increase it, means keep on training it, then there will be a case that it will able to classify with a means higher probability a particular class for this object. So one more thing, can anyone tell me why even by doing 2 times means four epochs of training we were not able to actually reach higher accuracy? Means the increase in the accuracy was less every iteration. Means the error, the loss function, the loss was not very high. Means very high every iteration. Yes, can anyone tell? What would be the reason for it? So exactly the reason is means this is a bit complex model because of means the input here given is it's not a binary image, it's a colored image. So and the network is big, and the size itself of a particular single sample is larger. It's a colored image. That's why uh, this every iteration we are not getting a very high loss. So this is I have few more examples in, but I'm stopping it here itself. Thank you.